Hello. Today we're covering regression analysis, one of the most powerful tools in all of analytics and one of the most unnecessarily feared. The math notation and the academic framing tend to intimidate people before they've even seen what regression actually does. So we're going to strip all of that away and focus on the core idea. Regression finds the relationship between two things and puts a precise number on it. By the end of this, you'll know what regression is, how to read the output, and why it shows up so often in marketing and research analytics. Let's start with the problem. Here's a situation that comes up constantly in data work. You have sales data, satisfaction scores, usage rates, churn numbers, and you have hunches about what's driving them. Maybe you believe that more advertising spend leads to more sales, or that users who engage early stay longer. A hunch is a starting point, but it's not evidence. The question is, how do you test whether the relationship you suspect is actually there? And if it is, how strong is it? That's exactly what regression is built to answer. Here's the core idea in one sentence. Regression puts a number on a relationship. Specifically, it answers the question, when X changes, how much does Y change? Not roughly, not directionally, precisely, with a specific number you can use for decisions, predictions, and planning. Once you understand that framing, regression finds the relationship between X and Y and quantifies it. The whole method becomes intuitive. Regression analysis is a statistical method that finds the relationship between one or more independent variables, the things you think are influencing an outcome, and a dependent variable, the outcome you're trying to understand or predict. The dependent variable is the thing you care about: sales, subscription length, satisfaction. The independent variables are the things that might be causing or predicting it: price, usage, ad spend. Regression measures how much the dependent variable moves when each variable changes. That's the whole idea. There are two versions of regression, and they're really the same idea at different levels of complexity. Simple regression involves one X and one Y, a single relationship you want to understand. Does week 1 workout counts predict how long someone stays subscribed? Multiple regression involves several X's and one Y, several factors examined simultaneously. For our example of Pulse app, a fitness app, do workout counts, plan tier, and notification settings together predict subscription length? Real-world research almost always uses multiple regression, because outcomes are usually influenced by more than one thing. But simple regression is where the concept clicks, so that's where we'll start. Let's make this concrete. Pulse app is a fitness subscription app. The team has noticed that subscribers who are active early seem to stick around longer. They want to test that intuition properly. Their question, does the number of workouts a subscriber logs in their first week predict how long that they stay subscribed? In regression terms, X is the number of workouts logged in week 1, and Y is the subscription length in months. Let's see what the data shows. We start with the visual, because regression is easiest to understand when you can see it. We take our Pulse app data, each subscriber in one dot, plotted by their week 1 workout counts on the horizontal axis and their subscription length in months on the vertical axis. There's scatter. Not every high workout subscriber stays forever, and some low workout subscribers stay a while. But a pattern is visible. The dots tend to climb from left to right. More workouts in week 1 seems to go with longer subscriptions. Regression is the method that formalizes that pattern and turns it into a number. Now regression draws a line through that scatter of dots, specifically the line that minimizes the total distance between itself and every data point. That's the regression line, also called the line of best fit. It's the single straight line that best summarizes the relationship across all the data, Some dots will be above it, some below, but no other straight line would be closer to all the dots on average. The math finds this line automatically. You don't need to draw it by eye. Your job is to read what it means. The most important thing to read from the regression line is its slope, how steeply it rises from left to right. That slope is called the coefficient. For PulseApp, the slope works out to be 1.8. That means for every one additional workout logged in week 1, the subscription length increases by 1.8 months on average. That's the relationship quantified. A steeper slope would mean a stronger relationship. Each additional workout would predict even more additional months. A flat slope would mean no meaningful relationship. Workout count in week 1 doesn't really predict subscription length. The coefficient is the number that tells you which it is. The regression line has two defining features: the slope we just covered, and the intercept, the point where the line crosses the vertical axis, which is the predicted value of y when x is 0. For PulseApp, the intercept is 2.3 months. That means a subscriber who logs 0 workouts in their first week is predicted to stay 2.3 months on average. That's the baseline, the starting point before workout count has any effect. It tells you that even the most disengaged subscribers tend to stay a couple of months before canceling, which makes sense. They signed up for something, gave it a brief chance, and then moved on. Now we can write the complete regression equation, which combines the intercept and the coefficient into a prediction tool. The form is y equals the intercept plus the coefficient times x. For PulseApp, subscription length equals 2.3 plus 1.8 times week 1 workouts. Let's use it. A subscriber who logs 5 workouts in week 1. 2.3 plus 1.8 times 5 equals 2.3 plus 9, which equals 11.3 months predicted subscription length. That's a specific actionable prediction based on one observable early behavior. You can estimate how long that subscriber is likely to stay. There's one more number worth understanding from the regression output: r squared, written as r to the second power. R squared tells you how much of the variation in y is explained by x. Essentially, how well the model fits the data. It runs from 0% to 100%. PulseApp's r squared is 0.62 or 62%. That means week 1 workout count explains 62% of variation in subscription length across subscribers. The remaining 38% is driven by other factors that aren't in the model yet. An r squared of 62% is actually quite strong for a single variable. It means workout count in week 1 is doing a lot of explanatory work, but it also signals that there are other factors worth adding to the model. That other 38% is where multiple regression comes in. In real-world research, one variable is rarely enough to explain an outcome fully. PulseApp believes 3 things together drive subscription length: how many workouts someone logs in week 1, which plan tier they're on, premium versus basic, and whether they enabled push notifications. Multiple regression includes all 3 variables simultaneously and estimate each one's contribution while holding the others constant. That phrase, holding the others constant, is the key advantage. It lets you isolate the effect of each variable fairly, as if you could change one thing while freezing everything else in its place. Here's what the multiple regression output looks like for PulseApp. 3 variables, 3 coefficients, week 1 workouts, a coefficient of positive 1.8 months. For each additional workout, subscription length increases by 1.8 months, all else equal. Premium plan, a coefficient of positive 3.2 months. Premium subscribers stay 3.2 months longer than basic subscribers after accounting for their workout activity and notification settings. Notifications enabled, a coefficient of positive 2.1 months. Subscribers who enable notifications stay 2.1 months longer than those who don't. Each coefficient tells you the independent contribution of that variable. And from a business perspective, the largest coefficient, premium plan at 3.2, suggests that plan tier might be the most powerful single driver of the three. Here's the most important caveat in all of regression analysis, and it's worth taking seriously. Regression finds a relationship. It does not prove that one thing causes another. For post-app, more week 1 workouts predicts longer subscription lengths. But why? There are at least two plausible stories. One, logging workouts in week 1 builds a habit, and that habit drives longer retention. The workouts cause the retention. Two, highly motivated people are more likely to both log workouts early and stay subscribed for a long time. Motivation is driving both things, and the relationship between workouts and retention is just a side effect. Regression can't tell you which story is true. It gives you the correlation. You provide the theory, the context, and ideally an experiment to make the causal case. Let's be balanced. The strengths of regression. It quantifies relationships precisely, giving you a specific coefficient rather than a vague, these seem related. It handles multiple factors simultaneously and isolates each one's contribution, which is far more powerful than looking at variables one at a time. The output, coefficients, R-squared, and predictions is widely understood across research and business analytics communities. The limitations, regression assumes a linear relationship, which isn't always the right model. Some relationships curve, and forcing a straight line through a curved data produces misleading coefficients. It's sensitive to outliers. A few extreme data points can significantly shift the line. Correlation is not causation, and it requires a meaningful volume of data to produce reliable estimates. Running a regression on 15 data points will produce numbers, but you shouldn't trust them. 6 things to take with you. Regression finds the relationship between X and Y and puts a precise number on it. That's the whole idea. The coefficient tells you how much Y changes for each one unit in X. It's the slope of the line, and it's the most important number in the output. R-squared tells you how much the variation in Y your model explains, how well the line fits. Multiple regression handles several variables at once and isolates each one's contribution by holding the others constant, far more powerful than one variable at a time. Correlation is not causation. Regression gives you evidence of a relationship, not proof of a cause. You need theory and ideally experimentation to make that leap. And regression is the statistical engine running behind price elasticity, key driver analysis, marketing mix modeling, and more. Understanding it makes all of those tools make more sense. Thank you for watching.